and share screen. Where is it? Okay, how's that? Can everyone see? So, I hate you all. So before we even get into the midterm, I guess into some of the questions, one of the questions was already asked was about Fermi energy levels. Where is it? There it is. When is the chance to find a hole above 50%? So to understand Fermi levels, you have to understand you have the energy levels, right? So this is as energy goes up. This is going to be our capacitance band. This is going to be our valence band. And this right here is going to be our EFI. That's your intrinsic value. That's your intrinsic Fermi energy level. And remember what Fermi energy level means is that at this point it is 50% filled. As you go up, it's filled with electrons. So as you go up, this is going to be less. You're going to have less than 50% filled. And as you go down, this is at T is equal 0. This is true at all temperatures. I'll show you the difference between temperatures after. So as you go down, it's going to be greater than 50% filled. This is true at all temperatures, right? So this works only at the intrinsic level. So that means a semiconductor that hasn't been doped either way. If we do dope the semiconductor, we're going to move the EF to a different level. Let's say here, EF. EF moves up. So we have our intrinsic level, that is a semiconductor that hasn't been doped at all. And we have our actual Fermi level, which is the Fermi level of our doped semiconductor. And this whole part shifts up alongside with that. So once again, below the Fermi energy level, you have greater than 50% filled, and above you have less than 50% filled. This intrinsic is just the baseline for when it is not doped at all. And that is always going to be half of the gap. So I guess this would be the full diagram that you would see in a Fermi energy graph. The only thing that would really move is the size of the gap and where the Fermi energy level is. Quick question, what are we covering today and will it be recorded? Yes, it will be recorded, and we're basically going to be covering over a whole host of questions, primarily theory from the midterms. So I'm basing most of the questions and answers based on the midterms 2018, 2019, and 2023. But this is only for electrons. So would holes be above 50% when EF is above EFI? Yes. So all of this stuff would be the opposite if we talk about holes. So so this is all electrons. If we were to talk about holes, so let's say holes, this would be 50% empty. That's what a hole is. A hole is empty. Above here, it's going to be bigger than 50% empty. And below, it's going to be less than 50% empty. And just so that appears on document, I'm going to write the electron, how it looks on the electron side. It's 50% full, less than 50% full, and greater than 50% full. So this is electron, and this is holes. So what happens when we change the temperature? What actually changes is not this information, but rather the slope of the actual percentages. So if we let's draw a graph here. Oops. So this is going to be the energy at the valence graph. This is the energy at valence, and this is going to be the energy at the conductance branch. And along here, and along this way, we're going to have the percent full. This is 100%, and this is 0%. So what happened? Okay, and oh, sorry. Let me just move these a little bit in so we can see what happens before and after. And we're going to have, say, the energy at the Fermi energy is over here, right? So let's say T is equal to 0K. What's going to happen is it's going to be at, how long do you plan on making this? As long as it needs to be, really. Usually how I aim to be is 8 hours. Until 8, not 8 hours, so 2 hours. Yeah, no, not 8 hours. I can't yap for that long. So T is equal to 0. It's going to look a bit like this. Now, I'm going to note here in a big black asterisk that how it would look like. There are no electrons or holes in the gap. So this is just illustrating how it would look like. Now, what happens, say, if T is at 300K? What would happen is it starts at 100, the same amount, but it curves down a bit like this. Oh, this is going to be 50%. So it's going to look a bit like this, if I can draw correctly. So that's what temperature does. As you increase the temperature, it flattens out, it increases this slope. It makes it wider, right? So at this point, it's not going to be entirely full. It's going to be, say, 90% full. And at this point, it's going to be only, say, 10% full. If we compare that at T is equal 0, it's going to be 0% full here and 100% full here. So that's what temperature does. So I'm sorry, I may have gone a little bit lost in the sauce. The question was, when is the chance to find a hole above 50%? Well, yeah, here you go. So holes are above 50% above the Fermi energy. They are below 50% below the Fermi energy, and the opposite for electrons. Are there any questions about this? Okay, I'm going to assume not. Oh, and one of the other things, as a standard, we define the capacitance energy at 0 electron volts, and the valence energy at negative EG. Because energy is all relative, it doesn't really matter what you define each one as long as it's correct, relatively speaking. So now we can get into some of the questions. One of the questions can I move this to another? Hello? No? Okay, I guess I have to open it up in a new window. Sorry about that. Open year 2 midterm. There you go. So, like I said, I'm primarily planning to go through more theory than number crunching because it seems like people have more problems with that. One of them I saw people were having trouble with was this one. So this is what do you call? Well, the question is right here. The figure shows four situations occurring inside of a current carrying wire. The arrows are meant to indicate the velocity of the particles. Assume all four wires are the same size and that all charges shown move with the same speed. So, what is the current? Well, let's assume a current direction. So let's say that to the right is where the current is flowing. For all of them, why not? What we really care about is the magnitude of the current, but we can calculate that afterwards. So when we have current, what happens? Our positive, say current is flowing to the right. What is happening to our positive carriers? They flow alongside the current. What happens to our negative carriers? They flow against the current. If we see the opposite of this, they're sort of opposing current flow. So what we see here is, so let's look at 1, for example. Let me show you. At 1, we have 2 positives and 2 negatives. These 2 positives are both flowing in the correct direction according to the current. That's going to be 2 current carriers to the right. And we also have 2 negative electrons also flowing in the correct direction that we want, to the left. So that's going to cause an additional 2 electron flows with the current. Sorry, I don't know how well I explained that. But I hope you can understand what I'm saying here is that positive carrier, for positive carriers to give current, they go alongside the current. For negative carriers to give current, they must oppose the current or go the opposite direction of the current. Negative charges flowing left can be treated as positive charges flowing right. Yes, that's also another way to look at it. So the flow in number 1 is 4. So positive go with current and negative go against. Correct. This always happens, by the way. So say if we have some resistor and the current is flowing this way, you will find that the negative end is on the other side of the current. And the positive end is where, flipped it around. There you go. So if you have a current flowing through a wire, the direction it's going to is the negative terminus, right? All of the positive carriers are going towards the negative terminus. Opposites attract. Likewise, the negatives flow towards the positives. Wire. So now let's look at number 2. We have 1 positive carrier going the direction we want, and we have 2 negative carriers going the wrong direction. They are opposing the current flow. So that's going to be -2 for a total current flow of -1. Remember, a negative current flow doesn't mean that a negative current flow just means that we've assumed the wrong direction. It doesn't mean we have literally negative current. It just means that the current's flowing the other direction than what we thought. Number 3. Once again, we have 3 positive charges going to the right. 3. And we have 1 negative going the correct direction as well. So +1. That's 4 carriers. And the final one, we only have 3. That's 3. So what is our current for each one of these? This one, it's 4. This one, it's 1 going to the left. 4 going to the right here. This one is 4 going to the right as well. And this one is 3 going to the right. Rank the conventional currents in the wires from highest to lowest, assuming current flowing to the right is considered positive. Well, Conventional current just means that we're comparing the magnitude of the currents, right? So we have 1 is equal to 3. They're both 4, right? Which is greater than 4, which is greater than 2. And we look here, it's number B. 1 is equal to 3, greater than 4, greater than 2. Well, I guess in this case, I'm not too sure, but I guess reading the question, it's asking you to assume that to the right is positive, so you don't take the magnitude of it, but rather just the value here. So 4, -1, 4, and 3. Yeah, I would do it like that in this question based on how it's written. So this is 4 is equal to 4, is bigger than 3, is bigger than -1. Any questions about that? Okay. So, thank you. The next question that I wanted to go over was, oh, here. This one is this one's a Fermi energy level question, so it ties in perfectly with what we did earlier. A semiconductor material is initially either p-type or n-type. Impurity atoms X are added to this material. The addition of X causes the Fermi energy to decrease. Hall voltages were measured before and after adding the impurity using the same experimental setup, and it was found that the two Hall voltages had opposite signs. Yeah, sure. Here you go, pasted. You may assume that in both the initial and final states, the semiconductor is strongly doped. Majority carrier concentration is much bigger than minority carrier concentration. So it's asking, is X donor or acceptor? And is the material initially p-type or n-type? Okay, well, let's draw it out. I don't know why it's telling me that. Let's start that. There you go. Did I? No. Whatever. So let's draw the Fermi energy diagram here. At this point, we're going to have the capacitance band. Here, we're going to have the valence band. And here, right in the middle, is going to be our EFI. I believe I forgot to state beforehand. But, oh wait. Yeah. This area is considered N-type. And this area is considered P-type. So if you remember, the EF level is the point where we have an equal amount of holes and electrons. So if we want to bump up the Fermi energy, we need to add more electrons, right? Because then we're pushing the amount of electrons further and further from the valence band because we're adding more electrons. So if we add more donors, the EF starts to rise up. Meanwhile, if we add more acceptors, we are now taking more, where acceptors essentially hog more electrons in the valence band. And so that will bring the Fermi energy level down. So as we add more acceptors, it's going to go down, down, and down. So what information does the question give us? It's initially either p-type or n-type. The addition of X causes the Fermi energy to decrease. So what is that telling us? That means that we have some EF, we don't know where yet, and it has gone down. This is EF after, this is EF before B. All voltages were, so right off the bat, we know that this is an acceptor. Right? So let me just highlight this here. The addition of X causes the Fermi energy to decrease. This means it is an acceptor. All voltages were measured before and after adding the impurity using the same experimental setup, and the Hall voltages had opposite signs. Remember what the signs tell us about the Hall voltage. The signs indicate whether it's an N-type or a P-type. If they had opposite signs before and after, that's telling us that the type changed, right? Because if it stayed the same type, the sign would be the same. The magnitude of the Hall voltage would change, but the sign would not. But it has changed. So we know that it has crossed the EF I band. It is crossed at this point, and it has gone down. So that tells us that it must have been N-type before, and the acceptor atoms turned it into P-type. Right? Anyone confused about that? All right, nice. So that tells us it was initially N-type. So this is before. This is after. And this is the addition of X. So X must be acceptor atoms, and the material was initially N-type. Anyone confused or have any questions about that? If X is an acceptor, is a material always going to be initially N-type? It's initially N-type because the sign swapped. Let me give you an example. Let's say that, so this is going to be EC, EV, and it's going to be EFI. Let's say that instead the question states that the sign never changed, right? Actually, we wouldn't know in that case. If X is accepted, material is always going to be initially an N-type. It's based on this question exactly, yes, but that's purely just because of this line here, that the two Hall voltages had opposite signs. Let's suppose that it was initially P-type, right? So this is EF before, and we add more acceptors, it just becomes more E-type, P-type, right? And likewise, it's possible that it was initially N-type, and we add more acceptors, and it still remains N-type. It's going to be less of an N-type, but it's going to be N-type still. The voltage of the Hall voltage only changes if EFI is crossed. EFI crossed. Only change signs. So it could have remained the same type, but the sign switching is what made it definitively N to P. Yes. Because it effectively tells you that it was crossed, and we know that it was crossed going down. So that means that it must have started above, ended under. Meanwhile, suppose it asks you to find how would you differentiate these two if you know that the sign doesn't change? How can you tell whether it's still n-type or still p-type? One way is the magnitude of the Hall voltage. Hall voltages increase as you get farther away from EFI, right? So as you dope more and more, your Hall voltage is going to get larger and larger. So in this case, the Hall voltage goes down, right? Because it's going closer to EFI. Meanwhile here, the Hall voltage goes up. Let me just draw the magnitude there so you don't get confused. So that's one way we could say, instead of saying that they had opposite signs, it has the same sign, but it gets, say the Hall voltage gets larger in magnitude. You now know which one of them it is. So is anyone confused or needs a little bit more than that? What if it was a donor? So, okay, the only thing that would change is the direction. Okay, so let me write here. Suppose X acceptor. No switch in sign. I want to write it out for the people who are just reading the PDF afterwards. So suppose X is donor. Am I a PDF file? No, that would be this document. This document is saved as a PDF file. I am personally not a PDF file. I'm a human being, as far as I'm aware. Not too sure about that one, though. So what if it was a donor atom? So the only thing that would really change, EFI, is that instead of EF going down, it would go up. Sorry, I flipped these around. Let me actually write it in a prime notation. So that's going to be before and after. So I'm writing EFA and EFB. A little bit weird in my opinion. I prefer this way. There you go. So yeah, that would be the change. And once again, let's say that the type switched, or Hall voltage switched. Then we know that this switch passed alongside the EFI. Oh, sorry, this donor pushed it across the EFI band. Let me move this to the other side here. And likewise, same thing here. This is going to be the P-type. This here is going to be N-type. So donor pushes up and acceptor pushes down, correct. And the way to think about it is that if you add more electrons, obviously the point at which you're going to, all the electrons are attracted down, right? All electrons are attracted down, but electrons attract down, but temperature keeps on exciting them to push them back up. So if you add more and more electrons, it sort of saturates the lower levels, and the electrons start creeping upwards and upwards. And the opposite for the acceptors. If you add acceptors, it starts basically holding electrons down below the valence band. So once again, this is Hall switched, and if we did Hall doesn't switch, so suppose X is donor, not switched, you have the same situation as above, right? You're going to have E. There you go. You can either have it like that or it's below, right? Oh. Either. And once again, you can pull the same magnitude of the voltage. Here, the magnitude of the Hall voltage is going up. And here, the magnitude of the Hall voltage is going down because it's approaching EFI. Remember, at EFI, there's no Hall voltage. At EFI, Hall voltage is 0. Same thing here. Two scenarios. So does that sort of make things a lot simpler for you? I'm outside right now picking pears off our pear tree and listening to this like a podcast. I respect that. We also have a pear tree and a cherry tree. It's very nice. So does anyone have any questions about this? Okay. Seems like that was explained well enough for y'all. Let's go on to the next question. One second, it's getting a little hot in this room. There you go. Just turning on the air conditioning. Okay, so the next question I wanted to go over was, oh yes, the electron energy level sort of stuff. Oop. There we go. And I'm going to post that in the chat for anyone following along. A free electron completely outside an atom is captured by a proton and ends up at the n is equal 3 orbit. What is the wavelength of a photon that is emitted in this process? So when we have a free electron, we assume it has no energy, pretty much. And then it gets captured by a proton. So it effectively falls into the proton's orbit. What is a sole proton? This is a hydrogen. I hope you all remember chemistry. A single proton and a single electron make a hydrogen. So what is the wavelength of a photon that is emitted in this process? Okay, so it ends up in the n is equal to 3 orbit. So it goes from a energy, or in the orbit of effectively infinity, right? Because it's completely free, to, this is 0 eV, to the third energy level. What's this energy? Well, we could use a formula. It's on your formula sheets. Let me pull it up. What the hell? PCS. This it? Yeah, here it is. We use this formula right here. Right? So the energy at some level, energy N, is going to be negative 13.6 electron volts over N squared. And in this case, it's 3. So therefore, the energy level of 3 is going to be negative 13.6 eV over 9 is going to be, what's that? Negative 13.6 divided by 9. You're going to get negative 1.51 electron volts. So it has gone from having an energy level of 0 to an energy level of negative 1.51 electron volts. That means that the electron has lost 1.51 electron volts. Where has the energy gone to? It's turned into a photon. Turns into photon. Remember the conservation of energy. We can't just lose energy without spending some energy. And whenever an electron gains or loses energy, it is pretty much always through light. If you shine light on it, it can absorb that light and gain energy, or it can lose energy by emitting light. So now the question is, what wavelength, if you look up here, what wavelength of light has 1.51 electron volts energy? Because that's what it's asking, what is the wavelength emitted by this? And we can go back to the formula sheet. In this case, the energy is equal to the Planck's constant, speed of light, divided by lambda. And there you go, you can calculate that. So that's going to be lambda is equal to hc over energy, which is equal to 1240 nanometer EV over 1.51 EV, which is equal to, what's that? 1240 divided by 1.51. You get 821. Let me just double check that I did that right. Yep. 821. Are there any questions about this? What happens to the negative side? That indicates that we lost energy. If it was positive, we're going from 0 electron volts to negative 1.51 electron volts. That means we lost 1.51, and so the electron loses 1.51. And so the photon must have 1.51 electron volts of energy. Right? This is conservation of energy. For me to lose some money, I must have given someone that money, you know? So electron always turns into photon and vice versa. It doesn't turn into a photon. It still exists. It just has turned some of its energy into a photon. Yeah, converted the energy. So if we were to make an energy diagram, so let's say this is 4, this is going to be 3, then 2, and then 1. Say energy diagram. And we are going to have infinity over up here. Oop. This is going to be 0 EV. This is going to be negative 1.51, and this is going to be negative 13.6. This electron came from up here and then jumped all the way down to position 3. And in it, it has released a photon of light. So negative 1.51 EV, and that energy has turned into a light. Everyone understands the energy diagram, right? Or should I go over it? All right, I assume not. It's very simple. It's just how much energy an electron has at that time. The only thing that might be confusing about it is the negative numbers. But remember, energy is all relative. Okay, so if there's no questions about that, we can go on to the next question. Theory question. Ooh, this one also relates to Fermi energy. We're doing a lot of Fermi energy. Sorry about that. I'll go over some of the other ones. This one's going to be real quick, though. In a semiconductor, electrical current is carried by free electrons in the conduction band only, free electrons and holes both in the conduction band, free electrons in the conduction band and ionized donor atoms in the valence band, free electrons in the valence band and holes in the conduction band, and free electrons in the conduction band and holes in the valence band. Okay, that's a lot. So the way to think about it, first of all, there's no ionized donor atoms, so you remove that. That maybe I don't really understand that option, but it's wrong. So you're going to have here, this is going to be your gap, and up here is going to be your conductance, and here's going to be your valence. So what happens when we are excessively p-type? For a p-type semiconductor, all of these are going to be holes. Pretty much. There's going to be like a spare electron lying around, but it's 99.99% holes. And now the question is, can this conduct anything? The answer is no, because holes can't move. Holes are fixed in place. That's what that's the whole thing. Electrons move around, electrons wave about, but holes always stay in place. What happens is actually in the valence band. Because here now you're going to have a decent mix of holes and electrons. And what happens is that these electrons are going to jump backwards. And if an electron jumps backwards, that's effectively the same as a hole jumping forward. So electron jump back, and the hole jump, in quotation, forward. Right? So we see that in a p-type semiconductor, holes conduct in the valence band, not the conduction band. Likewise, what happens when we have a very n-type? So this is your gap. Let me write that because we don't really care about the energy. We just care that it's a gap. There's nothing in between the gap. We have the conduction and we have the valence. And in the valence, we are going to have purely electrons, right? We're going to have very little holes. This is n-type. But in the conductance, we're going to have, again, a decent mix of electrons and holes. Those electrons are going to jump forward. The holes are going to jump back. Same as above. So, in an n-type electron where charge carriers, yeah, I can't write for the life of me. Are electrons compared to the p-type where the charge carriers are holes. You can see the holes conduct in the valence band, the electrons carry in the conductance band. And right there, free electrons in the conductance band and holes in the valence band. Does everyone understand how this works? Could you please repeat that last part one more time? Yeah, for sure. So this is going to be your p-type here. And we could see that the action of electrons moving back and forth, which is what carries the electrical current, is happening in the valence band. Nothing is happening in the conductance band because it's all holes. For electricity to be conducting, for electricity to conduct, it needs to have both holes and electrons. Because if it's effectively like a gridlock, right? If your highway is purely composed of cars, it's not going to get anywhere. So we can see in the p-type, all the action is happening in the valence band, and in the p-type, the charge carriers are said to be holes, right? If we compare that to the n-type, all of the action is happening in the conductance band because the valence band is completely full. So they're sort of polar opposites, right? So this here, no action. All holes. No action. All electrons. So in the n-type, the conduction has a mix of the holes and electrons. So those electrons moving in the conduction band conduct electricity. Correct. That's exactly it. So does anyone have any other questions about this? All right, perfect. Let's see one that's not Fermi Energy. That's Fermi Energy. That's Fermi Energy. I think I prepared too much Fermi Energy questions. This one's pretty good. This one is rather electron energy. So here we go. This is from 2019. This is from the 2019 midterm. The ones I've been doing have all been 2018 midterm. So 3. 2 hydrogen atoms are near to each other, but are still far enough apart that they do not have any effect on each other's energy levels. The electron in atom A is the n is equal 3 energy state, and the electron in atom B is the n equal 4 state. Okay, I'm not going to read out because it sort of gets annoying. We're going to write and read at the same time. So we have 2 electron atoms that are near to each other. And we have our little electrons floating about. That they're far enough apart that they don't affect each other. The electron in atom A, so let's design this as atom A and this is atom B, is the n is equal to 3 energy state. And the electron in atom B is the n is equal to 4 energy state. Suddenly, the electron in atom A makes a transition from energy level 3 to 2. So this one jumps down from 3 to 2. And it emits a photon. This photon is absorbed by the electron in atom B and is knocked out of the atom. So once again, here's the thing. So it's freed, right? This photon is absorbed by the electron atom B, knocked out of the atom. How much kinetic energy will the electron from atom B have after it is released from the atom? So the energy of this electron is equal to what? Oh, question. unrelated, but are you posting these slides after? I'm back and forth from watching and doing shorts. Yeah, I'm posting both the video and the slides. The video will take a while because I have to upload it, but and YouTube can be a little slow on that. But thank you. But the slides I can upload like immediately after. So this electron is freed. Okay, so first of all, we need to know the energy of the photon. We don't know the energy of the photon. Let's call this energy B. So this B after. So what's happening here is that the energy, so the electron has some energy, and it's absorbing the photon's energy. Now, some of that energy is used to free the electron. And you're left with the energy afterwards, right? You start with some energy, you get some energy, you lose some energy, and you're left with whatever's after, right? This is the same as kinematics. If you remember kinematic physics, all the conservation of energy questions, fun times. So, how do we calculate this? This one, we can just use the equation we used earlier. So that's going to be En is equal to negative 13.6 over n squared EV. In this case, we are at n is equal to 4, right? Yeah, n is equal to 4. So write that out, negative 13.6 divided by 4 squared. We get negative 0.85 EV. So our starting energy is negative 0.85 EV. Let me just put that off to the side here. So this is kind of like a collision calculation. It's a conservation of energy calculation. Am I a TA? I am not a TA. I'm a student. Like I'm taking the midterm with you on Wednesday. So then we have EP, the energy of the photon. What is the energy of the photon? Well, that's whatever this electron is losing. So EP is going to be the change in the energy of A's electron. So what is the change of A's electron? Well, it starts at n is equal to 3, and it ends up it starts in energy level 3, and it ends up in energy level 2. We can use this formula again, and we are going, what do we get? So we're going to get that delta EA is going to be negative 13.6 over 3 squared minus negative 13.6 over 2 squared. I may have accidentally flipped that. Let's see. I have 13.6, 2 squared. So change in energy of A is 1.89 EV. So this is also the energy of the photon, right? The electron has lost this energy and is all turned to the photon, which has traveled across and hit this electron. Okay, now the next question. What is the energy to free this electron? Well, freeing is essentially taking it from that level, from whichever level it is, in this case 4, and it goes to level of infinity, which is 0 EV. You can also do a calculation, negative 13.6 divided by infinity squared is 0. the limit anyway. You get the idea. So we're calculating from the level of 4. Let's write that here. E4 to infinity. This is also the change in B. Actually, no, it's not change in B. But so what is this amount? Well, we can calculate it. So E free is going to be E of 4 minus E of infinity. Or it would be would it be the other way around? Yeah, it would be the other way around. Sorry. It doesn't matter. If you get the wrong sign than what you're expecting, it's probably just because you flipped the order. Just flip it back. I don't concern myself with signs. I just figure out the sign after. Anyway, E free is going to be 0 EV minus negative 13.6 divided by 4 squared. That's going to be same thing here. 0.85 EV to free. Am I doing this correctly? Sorry. Sorry, I just need to check something here. Oh, I don't think I'm doing this correctly. Oopsie. What did I fuck up here? Sorry. .04 is... I wrote the answer, but I can't understand my own work. This course in a nutshell. Okay, I see the issue. This just shouldn't have been considered. We're going to set the initial energy. Energy is all relative. This is the annoying part. When we're at this level, energy is pretty much relative. So we assume that here EB is equal 0. It has no energy, and we're giving it energy, so that it bumps up, right? I hope that doesn't confuse you too much. Well, we basically start every one of these questions assuming that electrons have 0 energy. Why is it 0? Energy is pretty much relative. That's why. So whenever we start with these questions, we always assume that the electron, as it currently starts, has 0 energy in it. Usually, if it has energy, it just goes up to a higher level, or it shoots it out as a photon. So that it stays at 0 energy. So how do I explain this? Electrons don't like having energy. If they have energy, they will either jump, or they will emit electron, or they will emit light. And likewise, if they suddenly get, if they have too much, they'll give out. That sort of thing. And they'll just take in photons and, sorry. Wow, I explained that poorly. When they take on a photon, they're going to get energy, and they will immediately want to get rid of it. Because they are electrons, they don't want energy. And in this case, you can see that it gets freed. And it's going to end up with some energy. It's going to emit a photon right afterwards. So, sorry, let me note that. Assume electron or electrons, not assume. Electrons always start at 0 eV. They don't like energy. They will get rid of it. Either through emit light or increase what do you call it, energy level. So that's something to keep in mind. So now we have all of these parts in place. We have 0 plus 1.89 EV is equal to 0.85 EV plus EB afterwards. So we have 1.89 minus 0.85 EV is equal to EB afterwards. 1.04 is equal to EV. And like I just said, although it has this energy, this electron really doesn't like it and will almost certainly shoot it out as a photon in a fraction of a millisecond afterwards. So that it ends up with 0 electron volts of energy. Is that clear to you guys? Because I know I sort of switched things up and halfway through. Any questions? Okay, I'm going to assume not. We're going at a pretty nice pace today, or maybe because I'm just very used to doing electrical, and electrical takes fucking ages to do any question. Sorry, I shouldn't have sworn. Oh, here's another theory question. Why not? Oh, maybe question. I'm not gonna read that one out. You know, I'm deleting that. That's all right. In a semiconductor, the conduction band is a set of electron energy states which A, have energies less than the gap energy in a semiconductor, B, are completely full at 0 temperature, exist only as an n-type semiconductor, are always empty, and yada yada. Okay, let's go through each one by one. In a semiconductor, the conduction band is a set of electron energy states which... Oh, hey, it's a Fermi energy levels question. Sorry about that. This is going to be your conduction area. This is going to be your gap. Oh, sorry. Let me pause that. This is conduction. This is gap. This is valence. Okay, let me just... I need to start reviewing my answer just to make sure I'm not, you know, fumbling halfway through. Anyway. They have energies less than the gap energy in a semiconductor. Remember, the energy gets larger as you go up. So the way that we tend to write it is that this point has 0 EV, and this point has negative gap energy. Therefore, the conduction band is going to have more energy than the gap energy. Are completely full at 0 temperature. Okay. No. You remember back in the frontier, at 0 temperature, the conduction band is going to be completely empty unless the Fermi energy is somehow above the conduction band, which it, as far as I'm aware, doesn't. So because the Fermi energy level is always going to be within the gap, and because it's a hard cliff at temperatures equals 0, the conduction band will always be empty at T is equals 0 in a in a semiconductor. Well, it definitely won't be full. I'll tell you that. It will definitely not be full. Uh, no, no. EC is going to be greater than EV always. See page 1. Exists only in an N-type semiconductor. No. Conduction bands don't just disappear in a P-type. P-type. The only thing is that the conduction band is going to be completely empty. So it's not going to be doing anything. It's still going to be there. The holes are there. They don't just disappear. But the holes by themselves cannot do anything. In a P-type. Yeah, in a P-type. So holes don't disappear. Don't disappear. Are always empty at room temperature. This is just no. we know that for an N-type semiconductor to work, it conducts in the conduction band. We went over that earlier. Therefore, it kind of needs to exist. There kind of needs to be electrons in there. Can be occupied only by free electrons, not bound electrons. This one is true. So whenever an electron gets too excited and it jumps up from the valence, it becomes free. It's not really connected to any atom, and it starts to move around a lot. And that's a free electron. You could also determine that by process of elimination here. Can you explain D again? You forgot to list. Okay, so at room temperature, okay, you can also refer to the same graph here, right? So we drew this graph here at T is equal to 300K. And we can see that in the conduction band, there are electrons in here, right? Because there's going to be some spillover right here, this section here. It's not large amount, but it is some. Therefore, there are electrons in the conduction band at room temperature. That's also how N-types work, right? N-types require electrons in the conduction band to work. Okay. Any other questions about that one? Oh, my voice pitched up there. Is there any topic you guys want to particularly go over, like Hall voltage or more Fermi energies? 2023 question 8. Let me see. Oh, sorry. I can try, but I don't know. I don't have an answer written, so it's possible I might get this wrong live, and I'm gonna look like a fool. Where'd I get 2023 midterm? You can ask Paradise about that. I don't know. He gave it to me, but I did post it. I posted it in this channel earlier. I can post it again. Where is it? Did I lose it? There it is. You guys don't know how to scroll up. Bro's 2025 fall midterm. Insane. Okay. So once again, I haven't done this question beforehand. The answer is given, but I haven't done the question, so I don't know if I'm gonna make a fool of myself here. Its crystal of silicon has an acceptor atom valence 3 concentration of, I don't really think this part here, this valence 3 is really important. Concentration of 5 times 10 to the 15 centimeters to negative 3 at T is equal 300K. Oh yeah. Fermi energy position of this crystal is what? Okay. This one you're gonna have to do a little bit of sleuthing on the formula sheet. But I hope you guys know how to use the formula sheet at this point. So we're trying to find here Fermi energy. And we know the acceptor atom concentration. So that is the so that's going to be that our PO is going to be equal to, we can just assume it's 5 times 10 to the 15. We're going to assume that there's no, it doesn't say, so we're going to assume that there's no donor doping. And we're going to assume that this is much, 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 much greater than the NO. But you could pretty much do that almost all the time. So which one of these equations will let us find that? Well, it is going to be, if you look at the formula sheet, you are going to find EF minus EV is going to be equal to KBT ln of NV over PO. Okay, so this is silicon. We know it's 300K, so that's going to be EF minus EV is 0.026 times ln, we could just put it in our calculator, you know how it is. 0.026 ln of NV, you can find out your formula sheet for silicon at 300K is going to be 1.04 times 10 to the 19 over 5 times 10 to the 15. We are going to get 0.9, 0.1920 EV. So that means that the Fermi energy in compare is going to be 0.2 EV above the valence band. That's what this means. So 0.20 EV above the valence band, right? Very simple. That valence band. Now, if we look here, we have two options that are relative to the valence band. We have two options that are relative to the conductance band, and we have in the middle. This obviously isn't in the middle. Actually, we should show that. E gap is equal to 1.12 EV for a silicon. You can get that off the table. Therefore, the Fi, that's the middle, is going to be 0.56 EV. This is not 0.56 EV from either the valence or the conduction band, so we know it's non-deceptive. We have D and E, so we have 0.2 EV above the valence band. Both of these don't match it. Okay, so how do we put it in terms of the conduction band? Well, we could just substitute EV. EV is going to be 1.12 EV, negative 1.12 EV. Remember the diagram as I showed there earlier, right? If we go back up to here, the conduction band, is that a given? Yes, it is on your formula sheet. If we go here, right over here, and oh my god, it's sideways. But if you have it printed out, this is silicon here, right? So anyway, this is silicon here, and it's a little hard to read sideways, but this here says band gap energy of 1.12. I wish I had this the other way, but I have it printed in person, so I just look on that. So remember that that our conduction band has an energy of 0 eV, and the valence band has an energy of negative the gap. So if we add this up, our Fermi energy is going to be equal to negative 0.2 minus 1.12. That is negative 0.92 EV. This also means this is 0.92 EV below the conduction band, right? Because our conduction band is 0. And so negative value means you're below it, a positive value means you're above it. We could effectively add an invisible EC here because this is 0. What does NV mean again? NV? NV, we don't have an NV here. You mean EV? NV over PO. Oh, that's from your formula sheet. So NV over PO. PO is your number of electrons. Number of acceptor. We can assume that because we have so much acceptors, we can assume this is the value of PO. And that's much greater than NO, so we don't care about NO, but I don't think that really matters here. It's the effectivity of states in the valence band. Yeah, so NV is from your table. This is also from your table. If is PO the same as NA? NA. What is NA? Is that on? I believe so. In NA is the number of acceptors, right? Yeah, the number of acceptor dopers. I got written down that NA is the concentration of acceptor atoms. Correct. So in this case, we assume that NA is equal to PO because NA is so large that frankly, yeah, usually PO is equal to NA and NO is equal to ND. Yes. This is because this is engineer approximation, right? Usually we add so much acceptors that the base amount of acceptors and donors don't matter. Sorry, the base amount of electrons and holes in semiconductor don't matter anymore. So we can just approximate that Na is equal to PO. This happens whenever you just dope something by a large amount, right? If you're doping something and you're not doping the other way, and there's not like weird stuff going on, you can approximate this. God, thanks. Nice. So, going back here. So we now have, so this is 0.92 EV below the conductance band. Is that one of our options? It is. There's your answer. Is anyone confused or has extra questions on that one? All right, nice. Let's see if there's another question we can do here. or if anyone has another suggestion for what question to do. One, I was actually going to do a very similar question for that. Oh, is there a question that involved the effective mass on a midterm? I haven't seen that. Based on all of the three midterms we had before, I hadn't seen anything about effective mass. Okay, nice. Let me see. Let me just look over the work that I've done. Hall effect? Yeah, we can do that. Can I send over the midterms we're doing? The 2018 and the 2019 are up on D2L. The 2023 has been posted in this chat. You just gotta scroll up a little. Do you think it's worth doing any homework, or should focusing on midterms be sufficient to get half decent grade? I would say focus on midterms first. If you need more questions, do the labs. If you need more questions, do the homeworks. Memorize all the questions. You are not memorizing all the questions, brother. That I didn't solve. Hall voltage questions. Alright, sure, let's do a hall voltage question. This is the long answer question on 2018. And I'm just going to go through and post all of them all at the same time, so I don't need to go back and forth between doing all this. Determine charge carrier. Determine the density of charge carriers. Oops, sorry. I haven't even drinking any soda. I don't know why I'm burping. Crazy statement, but please don't do that. Okay, so a strongly doped silicon semiconductor is used in a Hall effect experiment with the parameters shown. Conventional current, magnetic field, slab dimensions. Okay, so first of all, whenever we're doing Hall voltage, actually most of the things, we're working in centimeters, not meters. That's something you really got to keep in mind. We are working in centimeters. Keep aware of the units, because sometimes we don't actually use SI units. In this case, you see here we're mixing centimeters, millimeters, and centimeters. That's bad. We don't like mixing types. So this here is going to be 0.2 centimeters. You should pretty much have that on like permanent radar. Whenever you are looking at stuff, you should be converting it to SI. Same thing here. This should be 30 milliamps. It's 30 times 10 to the negative 3 amps. Or 3 times 10 to the negative 2, whatever, man. The Hall voltage, likewise, is going to be 2 times 10 to the negative 3 volts. Very nice. I like how the profs do that to remind you how much they hate you. Yes. Determine the Hall electric field. At least we get the units on the formula sheet. We do, and that is very nice. Use them to your advantage. Determine the Hall effect electric field and use your answer to fill in the blank in the table above. Okay, so in this case we... Oopsies. Oh. There you go. So, now we need to determine the Hall electric field. So that is, what is the electric field coming across the Z? And it's sort of hinted at here because it says Z, you know. So, what is this electric field? Well, we know that this is going to be 2 millivolts. And this is, based on the voltmeter, you should know how to read a voltmeter by now. This is going to be 2 millivolts, and this is going to be 0 millivolts. Remember, the voltages are all relative. We could say this is 10 millivolts actually, and this is 12 millivolts, but make things easy. We'll pin 1 to 0. So, electric fields always point from the positive to the negative. This is a positive, this is a negative. The electric field is pointing up. So we know that's positive Z. Okay, what's the electric field? Real simple formula. You should actually really have this memorized at this point. I forgot what it was. Don't judge me. Right. E is going to be delta V over delta X. It's also linear, right? So the voltage here is going to be 2 millivolts, or, again, work in standard units, 2 times 10 to the negative 3 volts. And the distance over here, the Z direction, is 2 centimeters. We can verify we're using centimeters because if we look here, voltage divided by centimeters. So that's going to be 1 times 10 to the negative 3 volts per centimeter. Real simple. Real simple. Okay. Determine the carrier charge, positive or negative. Okay. Now we do the right-hand rule. Y'all know how to do right-hand rule, right? So we know the current is flowing this way. We know that the field is pointing this way. Now grab your right hand and start spinning it about and having a good time. And you will find that this is B. This is your positive charge. It's going to be going up. So the force for the positive is going up. And once again, you know how Hall voltage works. If you have the negative going backwards, those are also pulling up. That one's a little bit hard to see, but it doesn't really matter. You get the gist. So all of them are going to upwards. And therefore, this side is where all of the charges accumulate. What is this end positive or negative relative to the other side? It's negative. Therefore, it's negative. I hope that's simple enough. You guys know how to read a voltmeter, all of that. If this voltmeter was negative, you'd swap signs, all of that fun stuff. Determine the density of charge. You know, I'm just going to make this a bit simpler. Pull this down here. There you go. Determine the density of charge carriers and use your answer to fill in the blank in the table above. Okay, so this one might be a little bit tough. And what we do whenever we don't really know what equation might we be using, write down all the variables you know, all the variables you need to get. So in this case, we need the density of charge carriers. We know the current, we know the dimensions, we know, what else? We know the electric field, we know the magnetic field. Crazy statement, I'm not reading that out loud. And we know that the charge carriers are going to be, what do you call? They're going to be the E, right? Not 2.7, but 1.6 times 10 to the negative whatever. It's going to be the fundamental charge. That's a word for it, fundamental charge. Now, what is the equation that most closely relates these things together? Well, if you do a scan over on your formula sheet, you are going to find I equal NQ AVD. Now see that we didn't need to memorize what equation we're going to use. We write down what we have and we look at the formula sheet and we see what's most appropriate for the equation. There's a chance you might be wrong, but you'll notice when you run into a wall. Now we know we're trying to find N, we know Q, we know the area, we don't know the drift velocity. What is the drift velocity? Well, we can just look at the equation here. There's two equations actually. One is for whenever you have a positive doping or an p-type, and one for when you have an n-type. We have an n-type, so we are going to use the n-type one. So v dn. Does anyone in chat know what dn stands for? That's right. It's drift velocity as an n-type. Negative mu n times the electric field. Do we know mu n? We could find that on the table. Do we know the electric field? Of course we do. So now we can rearrange to find n. So that's going to be I over equal n q a negative mu n e. And we know that the charge here is going to be the negative fundamental charge because the carriers are negative. Q is equal to negative E. Let's write that. We know that the charge carriers are electrons, so it's going to be negative E. These negatives cancel out. I is equal to A, mu n, E is equal to n. Shove all of that into your calculators. So what's our current? We have 30 times 10 to the negative 3 over the area. We can, so when it says the area, that means the cross-sectional area of the current, right? This is area, which is going to be Z and Y. So it's going to be 0.2 times 2. That's correct, right? It might be correct. I did not write what the area is in my work. Okay. So it's going to be... Is that correct? Yeah, Y and Z. So what are these dimensions, man? They don't really match. Okay, 7 centimeters. Oh, no, they do match. I'm stupid. So, area is going to be Z times Y, which is 0.2 times 2. That's 0.4 centimeters squared. Okay, so now we can plug into calculator. So it's going to be 0.4, yeah, just 0.4 times 1350, if I remember correctly. I'm probably wrong. This is silicon, right? Silicon. 1350. Wow. I'm starting to memorize the constants. That's when you know that I'm beyond all saving. And our electric field is, what's that? That's 1 times 10 to the negative 3. We get... Did I put that in right? Sorry, 1 second. Oh, I just forgot E here. My bad, gang. Yeah. You pointed out just as I realized. Who needs E anyway? You know, one time when I was doing the question, when I wrote E, I accidentally put in like Euler's constant E instead of the fundamental charge. And it took me too long to figure that out. I was so pissed. That's what I mean. I make silly mistakes. Very silly mistakes. Yeah, I have my lab report due Thursday. I'm gonna get that knocked out over the week. It's really annoying. Anyway. Alright, awesome. It's still wrong. What did I fuck up now? How did I manage to do this? Okay, oh, that's why. This is not area. Oopsie. This is area. Because we're working in the Hall voltage, we're working with Hall voltage, Hall electrical field, we're using the area, the cross-sectional area, to the Hall stuff. And that means this. So this is going to be 7 centimeters. This is 0.2 centimeters. And that comes up to our area. So correction on this is going to be xy, not zy. That's going to be 0.2 times 7, 1.4 centimeters squared. Anyway, shove that into your calculator. Now you get the right answer. 9.92 times 10 to the 16. Sorry about that. And this is in concentration, so it's going to be centimeter to the power of -3. And we know centimeters because we've been working with centimeters. Everything has been in centimeters, so we should hope that our output is in centimeters. You can do all of the dimensional analysis. It's too hard. You have current, and I don't even know what's a unit for this, and electrical field, and area, and E, whatever. So, we have found the density of charge carriers. 9.92 times 10 to the 16. Suppose that now the experimental setup stays exactly the same, except now a current of 30 milliamps is passed in the Z direction instead of the X direction. The voltmeter will no longer read 30 millivolts. What will it read? Where did I put that? There. Okay, so let's draw a diagram. Whenever you're doing weird stuff, it always helps to draw what's actually happening. So we have our block here, big block. We still have our voltmeter set up. Negative, positive. What is it now? And the current is flowing upwards. Okay, so we're trying to find V. V is equal to what? And the current we know, so it's 30 milliamps. And once again, we're going to write that in SI. Okay, now what relates voltage and current? Ohm's law. So is Ohm's law. That's a shit R. Sorry. V is equal to IR. Do we know R? We don't know R. Can we calculate R? Let's see. Well, one of the formulas for resistance is on your formula sheet. R is equal to L over area times the conductivity. Do we know the length? Yeah, we know the area. Do we know the conductivity? No. Can we calculate the conductivity? Of course we can. That's going to be E. Where is that formula? I'm a little lost. There you go. Is N mu N plus P mu P. All right. First of all, we know that this is N type, and so we can assume that there's a lot more N than there is P. I'm trying to temper my swearing. Poor results so far, but you know. Right? Everyone knows why we cancel out P, right? So N type, N is much larger than P. Therefore, this part here is irrelevant. So to fill it back in, we get R is going to be equal L over A, N mu N. And we can fill that back in to V. So V is going to be IL over AN mu of N. We have all the values. Just plug and chug at this point. What do we get? So the area in this case is going to be this cross-sectional area. And if we go back to our original diagram here, that's going to be y along z. So area is going to be y times z, which is the same as last time. That is 1.4 centimeters squared. And our length is going to be our z. It's going to be our length, which is just going to be x, if I'm not wrong. Oop. No, it's going to be z. Wait, this is also wrong. What am I? sorry. It could be x, y. This is z. That's going to be 7 centimeters. We know everything. Plug and chug. So pull out a calculator. 30 times 10 to the negative 3 times the length, which is 7 centimeters, over the area, which is 1.4, times the number of the concentration of electrons, which is 9.92, times 10 to the 16, times mu of n, which is 1350. Did I fuck it up? Did I forget an E again? I did forget it. I keep doing this, man. Okay, still managed to screw it up. Uh-oh. Oh, that's why. Z is 2 centimeters tall, not there you go. See, I make a lot of very silly mistakes. It comes out all the way to the voltage is going to be 2 kilovolts. Now notice that is actually our initial reading. The reading does not change. That is actually if you do all the algebra, you will find that this is just an identity that is true. That if you do this stuff, the voltage isn't going to change. So, does everyone understand? Any questions? Listen, man, it's never cooked. It's never cooked. You just need to dedicate more time, you know? I believe in you. Love that question. Implies it does change. That would fuck. Yeah, the question implies that's going to change. Actually, this is this is actually written wrong. It's going to be 2 millivolts, and if you read it like that, the voltmeter will no longer read 2 millivolts. It reads 2 millivolts. Yeah, it seems like you did something wrong. It's correct. Can you explain B again briefly? B. Determine the carrier charge. This question. Okay. So whenever you have yeah, it's right hand rule. So whenever you have a current flowing down, and we're going to put B in this direction, right? Actually, let's just copy the diagram. It's easier. Let me. Oh. Big boy. All right. Here's your current. Your current's flowing this way. Your field's flowing outwards here. And that means that your force is going up here. If you test this for both positive holes and negative electrons, they're going to both be going the same way. They're both going up, right? So, naturally, this is going to be filled with the carriers. This is going to be filled with carriers. So what happens if, say, suppose that this is p-type? What would happen? All of this is going to be filled with positive carriers, right? And therefore, this is going to have a higher voltage than this area below. This will have a negative voltage relative to the top of it, right? And so we would begin to see, so if we hooked it up like this voltmeter, remember how voltmeters work, it expects the negative terminus to be lower than the positive terminus. If it isn't, it will output a negative value. In this case, it isn't, therefore, we're going to get a negative value. We're going to get some negative voltage. In this case, however, we have, or to give you sense, suppose that this was, I should be using white. There you go. So N or P-type doesn't affect the voltmeter. It does. I'll show you in a second, right? So let's suppose that we flipped these signs. You know, I'm going to show every single possible outcome here, just like I did last time. So let's say it's P-type. I'm gonna wrap up with this question, it seems like, because it's right reaching 8. So after this, we'll call it a day. So Hall effect scenarios. So if we have a P-type, it's all going to convene in the top. We're going to have and because the voltmeter expects this to be lower than the positive, you're going to get a negative outcome. Whenever the voltmeters, like terminuses, disagree with the actual reading, you're going to get a negative outcome. So in this case, you're going to get a negative voltage, right? Because a negative terminal is measuring a positive voltage. The positive terminal is measuring a negative voltage. Understand how that works? Now let's suppose that we flipped the voltmeter around, right? The terminals and the tightness affect the reading. So let's I'll show the N type in a bit because that's what our question was. I probably should start with that, but I just want to go over everything, right? About switching palm direction when it's N or P type. Am I recalling that correctly? Yes, whenever you're working with negative charges, you should be using your left hand. Whenever you're doing right hand, or whenever you have a positive charge, you should be doing your right hand. Now, no matter whether you do left or right hand, the Hall voltage, they're both going to go to the same direction. That's kind of the whole point of Hall voltage, right? So let's say that this is the terminal reading. We're going to get a positive voltage because our positive terminal is on positive reading. The negative terminal is on negative reading. Now, what happens when we flip the charge types? N types. N type. Well, if you do the Hall effect again, all of the charge carriers are going to go to the top. Our charge carriers are negative. So here it's going to be filled with negatives. And here is going to be positively charged. All right, now let's look at the voltmeter here. Will our voltmeter give a positive reading or a negative reading? In this case, it will give a positive reading because the negative terminal is measuring a negative charge. The positive terminal is measuring a positive charge. So they're in agreement. You're going to get a positive voltage. Could you go back to P-type? Yeah, sure. So here's the exact same scenario. The voltmeter is hooked up the same way, but it's filled with P-type. All of the charge carriers at the top are going to be positive. Based on right-hand rule, they're all going to the top, and it's P-type. So it's positive. And the negative terminal is measuring a positive charge on the top. So it's going to give you a negative reading. Yeah. Okay. What the? There we are. I don't know how I did that. And likewise, over here, we're going to have same scenario again. What do I use to study? I just did the midterms, man. I just go over the midterms. If I see something I don't understand, I try to search up, and then I just repeat. So, N-type. Once again, all of the charges go up here. We have a negative charge on top, but our voltmeter is hooked up as if it's a positive charge. They are in disagreement, we get a negative voltage. Is that clear? So that these are all of the possible scenarios you are going to get with Hall effects. So in this case, we had so in this case, we didn't know what the charge was at the top. We knew that all the charge carriers were going to the top based on right-hand and left-hand rule. All of the charge carriers are going to the top. But we don't know what the charge carrier is. But we know that the voltmeter is positive. That means that the voltmeter must be in agreement with whatever that it is. So the positive terminal must be hooked up to the positive end. And the negative terminal must be hooked up to the negative end. If this was negative, we knew that these terminals are wrong, and we would have to swap it. Is that clear? Man, I already forgot who actually asked the question. I'm sorry. Java 8 runtime environment. Good name. So are there any more questions or any other things anyone wants to go over? But yeah, going over studying, I can't provide too much info because everyone studies differently. But personally, I just go over each question. If I find something I don't understand, I just look up and review it. How many midterms did I do? I did one so far. I finished 2018. I did a couple. I did like 3 or 4 questions from 2019. And I think I did 1 question from 2023. That is also all the studying I've done so far, if you're going to ask. Okay, so I think we can wrap up the tutorial here. Thank you all for coming. I hope this has helped you. Seems like it has for some people. And I'm going to be uploading the PDF shortly and the video afterwards. All right, thank you all. Let me just pause the recording there.